Hello everyone, this is Jiahao. In this video, I'll demonstrate how I implement my code in details. We'll start with the successor function, which is a very important part of our implementations. So in my implementation, the successor function allows the user to pass two arguments, which is one is the passive, which is the list of elements to describe the initial state of the puzzles. And it's just a simple Python list following the order of this. And the weight, just the Boolean variable, allows the user to decide whether they want to output the weights. In my implementation, of course, you always want to do that. And the transverse function is just the function to allow the user to arrive the actually compute a pass after the exhaust the searching. The finish the searching. The print pass function is an interface and allow the user to input the solution path and output the each moves at each step, and of course two heuristic functions. We'll start with the breadth first search. So one of the most important part of breadth first search is to avoid duplicates. To do this, we first create this visited function, visited variable, which is a Python hash set. And every times we pop a node out of the heap here, those two lines. Then we just then we add that node into the visited hash set. So once we have created different successors, we check if this successors in the visited. Of course, we also check the successors in the predecessors. Predecessor is a Python dictionaries that contains information of all the child nodes and all the child nodes we have ever created along with their parent nodes. So if a successor is inside the predecessors, it means like it's been created before. So we don't want to add that to the heap again. Depth first search is similar to breadth first search. The only difference is now instead of using the heap, we use a stack. So a stack allow us to pop from the end of the list instead of the beginning of it, and everything else stayed the same. This is a non-recursive implementation of depth first search. Iterative deepening is a bit special. So because it has a depth limit for the stacks. So now the stack, instead of using a Python list, I use the Python dictionary, with its keys being the depth level, and the values being the stacks corresponding to each depth level. So every time we check if the current depth layer have been run out. If it runs, we just go to the previous layers and pop the nodes out of that stack. Yeah, of course we check for duplicates. So uniform cost of in this one we create this G cost, which stands for the move cost from the initial route to every single node we visited. And to avoid duplicates, of course, we first check for visited nodes, and also we checked if the successor is in G cost. If it's in G cost, that means that successor has been created before. We don't want to add it. We don't want to add it. And of course, we want to update the distance information if we find a smaller distance. So best first search is similar to uniform cost. The difference is now instead of using the move cost from initial states, we check the heuristic costs, which is over there. We calculate distance by using heuristic costs, and we pop the one with the least heuristic cost from the heap every time. So A star is a combination of sort of like both the move cost and the heuristic cost, and everything else pretty much stayed the same. The only difference, the distance. Now instead of calculating using heuristic and move cost alone, now we use both. This stands for the distance from the current node, and we just weight plus the function weight, the current weight, and then of course the heuristic. Yeah, and then we update relevant information if we actually find a distance that is less than the previous stored one.